For this video, we're looking at the next derivative of a logistic function. So let's say we have some rate of change of population growth, the rate of change of population with respect to time, and I want to take the derivative of that. Well, I'm going to take the derivative with respect to time. So I'm taking the second derivative of population with respect to time. So let's start with this equation here. dp dt equals 3p minus p squared over 6,000. That's your first derivative. Now I'm going to take the derivative of both sides with respect to time. Now notice that these are not t's, they are p's. So I'm going to have to actually use the chain rule. These are like my u's, and then the derivative of my u will have to be multiplied in. So this will equal, and then the derivative of 3p would be 3 times dp dt, because I'm taking the derivative with respect to t, minus, I can bring the 2 down, which will cancel out with the 6,000, making it a p over 3,000 dp dt. And that is my derivative here. Now, if I actually factor out a dp dt, I get 3 minus p over 3,000. Well, this dp dt here is this right here. So I have 3p minus p squared over 6,000 times a 3 minus p over 3,000. Now there are all different kinds of ways that we could have done this. I could have used the factored form. I'd already actually transformed this equation a little bit. I could have done all kinds of different things from the last video, but I just wanted to show you a direct approach. Okay, so if I wanted to know when the second derivative, and this is my second derivative from up here all the way down, when it's positive or negative, I could actually just set this equal to 0, each factor equal to 0. And again, I know that I could factor out another p from this one. I'm going to go ahead and do that so you can see it. So there's a p factored out, and I'm leaving everything else just pretty basic. So it's 3 minus p over 6,000 times 3 minus p over 3,000. So if I set each factor equal to 0, I have p equaling 0 being important, and it should make sense that a population of 0 is going to be significant because it's not going to grow if you have something there. Then if I set this factor equal to 0, 3 minus p over 6,000 equals 0, I can multiply everything by 6,000 or just add the p over 6,000 here. So let's do that. 3 equals p over 6,000 multiplied by 6,000, and the population of 18,000 is significant, and from our last video we know that's the carrying capacity, so it should be significant. For this one, I have 3 minus p over 3,000 equals 0. Add the p over 3,000, I have 3 equals p over 3,000 multiplied by 3,000, and I have a population of 9,000 also being significant. And one thing to note is that this 9,000 is half of our carrying capacity from this problem of 18,000. And Logistic will always work the same way. So you're going to get a significant number that is halfway to your carrying capacity. So if I look on my number line and I mark my significant points, I have 0, I have my carrying capacity of 18,000, and I have halfway to my carrying capacity 9,000. And I'm looking at the sign of my second derivative. So if I pick a number in here, like say 4,500, and I plug it in, I'm going to have a positive times, now 4,500 over this makes a fraction less than 1, so 3 minus something that's less than 1, another positive, times, and then 4,500 over 3,000 is more than 1 but less than 3, a positive. Positive times a positive times a positive tells us that that will be a positive number. my second derivative is positive, my function will be concave up in this interval. If I pick a number in here, let's say 10,000 or 12,000, it doesn't really matter. My first factor is going to be positive. And let's say that I'm picking 12,000. 12,000 over 6,000, I'm sorry, it's 12,000 squared. No, down here. Okay, 3 minus, and it's 12,000 over 6,000, that's 2, so that's a positive. And then 12,000 over 3,000 is 4. 3 minus 4 is a negative. A positive times a negative is negative. So my function will be concave down in this interval. At 18, after 18,000, I pick something like 20,000. So I have a positive times. Now I can pick any number I want, so you can imagine I can make this fraction huge. So if I do 3 minus that fraction, I'm going to get a negative. And the same thing over here, 3 minus something that can be really huge, a negative. So a negative times a negative is positive times a positive is positive. So my function would be concave up on this interval. So if I was going to sketch a graph, I know that my important numbers were, and this is population over here, and time down here. So 18,000 is important. And I know 9,000 is important. And 0 is important. So what I know is that from our previous first derivative, I know that if I have any population starting down here, my population is going to increase to the carrying capacity. If I start with the population above, it's going to decrease towards the carrying capacity. So I'm going to put a dotted line on my carrying capacity. Well, from 0 to 9,000, if I have a starting population in here, I know that it's going to be concave up until it gets to a population of 9,000 and then be concave down afterwards, which makes sense. It's going to have to go up and then eventually turn because it's going to have to level out at the carrying capacity. If I start with a population between 9,000 and 18,000, it's going to have to go up. Our first derivative was positive, but we're already in the leveling out stage, so it is concave down. Then the sad story is that if you start over something 18,000, some starting population up here, our first derivative is negative, which means our population is dying off. And it's also leveling out, so it's headed towards the carrying capacity. So you can see that it is also concave up. So those are our 3 possible logistic curves for some population over time.